A double mass spring mechanical system is shown here. We want to analyze it and find a solution for displacement of mass m1, which means x1, and mass m2, x2, using Laplace transform. So it's basically an example to illustrate how Laplace transform can be used to make life easier in terms of analysis of this mechanical system. All right, so we have this placement of m1 and m2. We make the assumption that the surface is frictionless, so friction is not a concern here. We have the displacement of the mass m1, as I'm going to show it. So we have the displacements of mass m1 as x1 shown here, and we have the displacement of mass m2 shown here with this direction. We make the assumption that up to the time t equal to 0, these masses m1 and m2 are held in place, so they're not moving. And suddenly at time t equal to 0, we let them free. So at time t equal to 0, now it's just a matter of application of all forces to m1 and m2 and figure out the displacement. So starting at time t0, masses can move freely. And as you can see, we have a spring K1 here. So with a spring constant K1, we have damping factor B1 here, and then, or damping coefficient. We have spring K2 with a spring coefficient K2, and also damper or damping coefficient B2 here as well. So the only force that is forcing or initiating the movement here would be as soon as we leave the M1 and M2 free, then the gravity kicks in, and we have M1g, force of gravity on M1, and we have the same thing, M2g. So that is also applied to M2. Again, the surface is frictionless. So in order to find the proper equation for displacement, we use Newton's second law, and that says the sigma of all forces applied to a mass should be equal to the mass times the acceleration. And acceleration is the second derivative of displacement, or x1. And let's use this notation that second derivative is just represented by this notation x1 dot dot. So that basically means, just to make sure we are on the same page, that basically means the second derivative of displacement with respect to time. And of course, if it is a single dot, that means the first derivative, which becomes a speed. Okay, so in this equation, I'm going to just quickly write what I see. So the sigma of forces should be equal to this. What are the forces for mass m1? We have k1 that is counteracting the movement of x1. So as a result of that, we have negative, if the direction of x1 indicated positive direction, then negative k1 times x1 is the force that is applied by spring number 1 to counteract the movement of x1 or displacement of x1 for mass m1. Now we have the same thing. This damping factor placed here would actually counteract the movement, so but proportional to the speed of m1. So this one we will have negative b1 times the first derivative of displacement, which is a speed with respect to time. x1 is a function of time. It's not shown here, but there's an argument of time for x1. Okay, so the other thing we have is, of course, m1g as shown here. So you can break down m1g into two components, obviously. So one is the, so let me show it this way so that it's easier to be seen. For both, for each of m1g or m2g, I can write it this way. So let's say this is your m1g force. It can be broken down into two components. One, projection vertically applied to the surface of interest here, which is if this angle is theta, then this angle here will be theta. So what you see here is m1g cosine theta. And the other force that we have here, of course, is, as you can see, this force, which is the projection in parallel with the surface that we have here. And of course, if this is theta, what we have is this will be our theta. So let me just make sure I'm not missing something. In that case, what we have is, okay, this is m1g sine of theta. Because if theta is 0, of course, the sine of theta becomes 0, then there is no force, because if the surface is flat, not tilted like this, then there is no component of m1g that is going to be applied across or in parallel with the surface. So we have m1g sine theta. Okay, so what I was about to say, that this m1g sine theta is the portion of the m1g that tries to move m1 and is a force that pushes m1 in parallel with the surface. So we have this is equal to, so we have a plus m1g sine theta. And what else do we have? We have also this k2 that is going to again counteract the movement for, so let's say if x1 is moving this way, k2 is pushing backward, and if x2 is moving this way, k2 is again pushing against the movement of x2. So what's going to happen is it will be like this. So if, as I said, we have negative k2, and then we have x1, and then we have uh, negative x2. And finally, what we have is also the effect of this damping factor, so that would be minus v2, but then it would do a counter force proportional to speed, which is x1 dot minus x2 dot. And then the result of all these things applied together will be equal to, just as is mentioned here, m1 times acceleration for m1, which is second derivative of displacement x1. Okay, with that in mind, I can let's keep this as equation number 1. But if you want to make it cleaner, one thing I can do is I can just maybe rewrite it this way. So I'm going to change the color so that it's easier to be seen. So what I can write is keep m1g sine theta on one side, and maybe move everything to the other side of equation so that it looks nicer. So what we have is m1 x1 dot dot, and then so second derivative, and then plus all the components. As you can see, I have um, maybe just to simplify, k1 plus k2 times x1, and what else do I have? I have minus k2 x2, and I think I have b1 x1, that's dot, that's the speed, and I missed b2 as well here. So it's b1 plus b2, and then times x1 dot, first derivative with respect to time, and then we have minus from here, b2 x2 dot, and plus m1 x1 dot dot. So the second derivative. So let's keep this as equation number 1. For we can write the same thing, sigma f for mass number 2. So if we write it, then we get this outcome. We have again Newton's second law, sigma f for the second mass should be equal to m2, the second derivative of the displacement for the second mass with respect to time. So that's the acceleration of the second mass. So if we just again write whatever the sum of all forces, same thing, m2g, the portion of m2g that tries to force m2 into direction of x2, again, starting at time t0 that we let go of mass 2 will be equal to, and it's important to make sure we understand that these at time t equal to 0, we are letting go of these masses to start moving. So it's as if suddenly there is this force that is applied to masses. Okay, so what is happening is um, sigma f. So if x2 is moving this way, k2 is counteracting, and also b2 is counteracting. So what I'm going to get is k2 proportional to displacement, so it would be x2, but then minus x1, and that's the k2. The impact of b2 will be the same way, but proportional to speed, so it will be x2 dot minus x1 dot. And the reason for this is, imagine if in an imaginary scenario, in a hypothetical scenario, if m2 and m1 move at the same displacement amount, then k2 and b2, they don't, I mean, k2 doesn't feel anything then, because k2 is proportional to delta displacement between the two ends of it. And if x2 and x1 move the same amount, k2 doesn't see anything. That's why it has to be proportional like this. The same thing about speed. That's why you see that b2 is multiplied by uh, um, just to make sure I'm not missing something. So uh, it's important to notice that it should be a negative sign here that I missed. So it should be a negative sign here, of course. So making sure that I'm not missing something. As I said, the direction indicates that the force applied is countering the movement. So if x2 and x1 like this direction means positive, then the force will be the other way. So force would be like this. The force applied by the spring and also by the damping. So these guys, and what we have as well for sigma f is now in the positive direction, we have m2g, and then we have sine theta, and should be equal to now m2 and the second derivative of displacement for mass 2. Okay, again, just to, I think it's good enough in this sense, but we can apply the Laplace transform to, say, equation 1 here. So let me apply the Laplace transform to this equation. And let me apply Laplace transform to equation 2. The reason for that is these equations are dealing with derivatives, and it's not easy to deal with them. But by transforming them using Laplace transform, we get into a simple algebraic scenario in which we just deal with the division and multiplication by the nature of Laplace transform. Just one reminder, these forces, m1g sine theta that I shown here, as I said, we are keeping this mass m1 and m2 in place up to time 0. Suddenly at time 0, we are letting them free. So it's as if suddenly at time 0, this m1g sine theta is applied. So effectively, while it's not shown here, it's as if we have a u of t, which basically says up to time 0, this force is not there, and at time 0, suddenly the mass feels that force onward. The same thing about m2g sine theta. Effectively, you have m2g sine theta times u of t. U of t is unit step function. So it's as if up to time 0, that force is not there. Suddenly, starting at time 0, that force appears. Okay, so with that in mind, what I can do is rewriting equation 1 using Laplace transform becomes this. So it becomes m1, let's just write this one, assume that we don't have initial conditions, so m1 s2 x1 as a function of in S domain, and then we have plus k1, and we have plus k2 times x1, again, I'm not going to write, but it's a function in S domain, and we have negative k2 x2, again x2 of s. I'm writing it like this because it's the first time I'm showing x2. And finally we have b1 plus b2 times x, that dot x1, it becomes s x1 of s. I'm not going to show the argument. And we don't have initial condition. So minus b2 and dot x2 becomes, x2 dot becomes x s times x2, and finally we have m1. I think I wrote it twice, so let me just remove this one because I wrote it twice. So that's my equation number 1, and I'm gonna move this to here. Okay, so no need to write it twice, and let me just clean this up. Okay, so I think I took care of everything that I needed, meaning that all the components that I had here are taken care of. And finally, as you can see on the other side, I have m1g sine theta u theta ut. So it's just as simple as m1g sine theta divided by s. S 1 over s is the Laplace transform of u of t. So that's now my equation number 1. So let's say equation A. Okay. I can do the same thing for equation number 2 here. So what I'm going to do is I'm going to write it as m2 s because it's the second derivative becomes s squared, and then x2 of s plus. So it's as if you move these guys to the other side, so it become I think it become, as you can see, k2 x2 plus k1 um, minus k1, so minus k1 times x1, just to make sure I'm not missing something, minus k2 times x1, because as you can see, it's plus k2 times minus x1 become plus k2 x1, but we are moving to the other side. So minus k2 times x1, and then we have plus v2 s x2 of s, and we have minus b2 s x1 of s. So all these four components are moved to the other side, plus the one that I took care of, and finally what I have is just m2g sine theta, and the Laplace transform of u of t is 1 over s. So m2g sine theta divided by s. This is my equation B. Okay, we can rewrite this whole thing using matrix representation. So it would be as easy as just, you can see that I can package x1, all x1 into, say, a vector like this. I'm going to write it quickly and then I'm going to explain. Maybe that's easier. m1 is times s squared plus, uh, let's say, b1s, b1 plus b2sx, so b1 plus b2 times sx1, and finally we have k1 plus k2, and then we have times x1. Of course, I'm not going to write x1, so that's about it. For the other one, we have b. Okay, got it. We have negative b2 s, and then we have negative k2. That's it. And for that's the and imagine I write it this way, but imagine this is multiplying a vector that contains x1 of s as a basically x1 as a function of s and x2 as a function of s, and that's it. The outcome is equal to the right hand side, which is m1g, and you know what? I'm going to factor 1 over s from this whole thing. But if you like, we can factor it more than that. But maybe what I can factor is g sine theta over s times m1 and m2. So that's the other side. And finally, for the second row in this matrix, I have now, um, as expected, it should be a symmetric one with respect to these entries. So it should be minus b2s x1 and then minus k2 x1. And this is the busy one. So I mean, busy one in terms of more involved than the first entry here. So it would be m2 s squared because of this one, times x2s, which is taking care of that side, and then we have plus b2s x2, and finally we have plus k2 x2. Maybe I can just make it in a more congested fashion so that it's easily observable. So what I mean is I have plus K2 and then plus B2S and then plus, just to make sure I'm not missing something, there you go, plus B2S is taken care of, and then finally I have K2 is taken care of, B2S is taken care of, and finally I have M2S squared. Okay, so I have my two equations represented into using the matrix representation, and then the solution for that can be easily found using Cramer's rule, for example. So what we were looking for, let's say, is changing the color so that it's visible now. What we were looking for is, let's say, the value of x1, for example, to be solved via this equation. So x1 of s is equal to maybe to just show it in an easier fashion. Okay, so it Kramer rule says determinant of, let's say if this is your matrix A, so let's say this is your matrix A, this whole matrix that you can see here, this matrix. Let's say this is matrix A, it's a 2 by 2 matrix, and so Kramer rule says determinant of matrix A, and in numerator you will replace the first column with what you see here, basically g sine theta divided by s times m1 m2, and then you just multiply. So what you're going to get is determinant of that matrix, so g sine theta divided by s divided by s, and then multiplied by. Okay, so that's going to be multiplied by m um, m1 and then multiplying m2 s squared plus b2 s plus k2 and um, plus m2 times the negative of this guy, so b2s plus k2. Okay, that's the solution basically. So what happens is, of course, determinant of A is more involved because you end up with multiplying this entry with that entry. That gives you a fourth order polynomial in S, which involves S to the power 4 and so on and so forth. So it's not easy to solve, but basically we found our displacement um, as we needed in S domain, and then we can just analyze it. The same thing for x2 of s. So you can write x2 of s in the form of, again, using the Kramer rule. This time, the denominator is the same thing as I wrote here, so it would be determinant of this matrix A, and which is basically, as I said, this busy entry multiplied by this one, and then minus the product of these two guys. So for numerator, in the Kramer rule, we're gonna replace the second column with, again, this gc sine theta divided by s times m1 and m2. So the outcome, and then take the determinant, the outcome would be just, again, g sine theta divided by s times, okay, so this time we have m2 multiplying this guy, so it's gonna be m1 s squared plus b1 plus b2 times s, and plus k1 plus k2. So that's one argument we have. And the second one would be negative of this one, negative of this entry multiplying m1. So that becomes plus m1 times, um, let me shift things a little bit higher so that we can see the, okay, times I'm going to shift it later. So times B2S plus K2. Maybe just a little bit less congested. So times B2S plus K2. And that's it. This is my numerator. Okay, so what I obtained here is a very interesting outcome that shows we can find the solution for the displacements x1 in S domain and x2 in S domain this way for this system, for this mechanical system, and Laplace transform helped us by converting the second order differential equation into a simple algebraic relationship that we could easily solve, at least to find the x1 of s and x2 of s in the form of a rational functions with polynomial in numerator and denominator in s. I hope that this is helpful.